Welcome again. So, we'll be discussing now two important properties of continuous time LTI systems through this characterization, which is in terms of convolution integral. And first property we'll be discussing is the property of causality. Now, we have earlier discussed in the first chapter the property of causality, wherein we discussed that a system is causal if its output depends only on the current and the past input samples, right? Now we'll try to remodel the same thing, how we can express this causality in terms of the impulse response. And now that we have defined, characterized our LTI system in terms of the impulse response. So as per our characterization, the output of an LTS system is expressed like this: minus infinity to plus infinity, then h of tau, x of t minus tau, d tau. Yeah, the other way around. You know that this convolution is commutative, so you can also put it like x of tau into h of t minus tau. But for this analysis, for expressing the causality, this is more apt, this representation of the convolution, right? So what I will do is I will just break this integral into two parts. First one from minus infinity to 0, h of tau, x of t minus tau, d tau. And the second integral will be from 0 to infinity, h of tau, x of t minus tau, d tau. Fine. Now, for a system to be causal, the output, it should only depend upon the present and the past samples. Now if you take this integral, the first one here, fine, the integral is with respect to tau, so the limits are for tau from minus infinity to 0. Okay. Now in this I am having this term x of t minus tau with tau from minus infinity to this. Fine. So this means tau will have all the negative values, minus infinity to 0. So which means ये जो आपका term है, it will be x of t plus tau, because t will have only negative values. Fine. So to make it more, it should be less than 0. Fine. Okay. So you will get values like x tau plus t plus 1, t plus 2, t plus 3, which are, this is basically future samples. So इसमें use नहीं, we can say values of input, because we are defining at the time t, so it is having values x of t plus something. So this means that these values of your input you'll be getting in the future. Now from the definition of a causal system only has dependency on the current, that is x of t, and the past inputs, that's x of t minus tau. Now this integral clearly indicates the presence of future input values, right? So I can conclude that for any LTI system, to be causal, I have to ensure that the portion, that the part that contains the future input values, it should be 0, right? Because if it is not equivalent to 0, then it will have dependency on the future input value. So in other words, it means for an LTI system to be causal, this first integral from minus infinity to 0, h of tau, x of t minus tau, d tau, it should be equivalent to 0. Okay. Now in this integral, I have two quantities. I have the impulse response and I have the signal in the signal at this future value. So it means that this equation basically means that either your h of tau or x of t minus tau should be 0. Right? Now x of t minus tau, it is basically an input and it cannot be 0. In general, you can't generalize this because it doesn't make sense. If your input is 0, then you're not interested in the response. The system gives only a response when there is some applied input. Right? So this means, so since x of t, in general, it may not be 0, so we can conclude a very important result here, that since x of t, it may not be 0, therefore for a continuous time LTI system to be causal, h of tau, it should be equivalent to 0, but for, because it is for this condition. दूसरा इंटीग्रल तो आपका पूरा है यहाँ पे, for tau less than 0. Fine. So we can say that a continuous time LTI system is causal if its impulse response is equivalent to 0 for t less than 0. This is a very important result, right, for causality. So general system के लिए a system is causal if it only depends upon the current and the past samples, and for an LTI system characterized by impulse response, and it will be causal if and only if its impulse response is 0 for time less than 0. Okay. So it means if I have a, therefore I can say, therefore a causal continuous time LTI system, it is given by, अब अगर आपका LTI system causal है तो ये part तो गया because it will be 0. So you will be left with only other part, that is y of t is equivalent to 0 to infinity h of tau x of t minus tau d tau. Yeah, you can express it because it is a commutative operation, so you can very well express it as what you call, yeah, we will do the analysis here, so ये थोड़ा ज़्यादा ये हो जाएगा. So here different system, so I have my causal LTI system expressed as y of t is equivalent to 0 to infinity h of tau x of t minus tau d tau. Okay, so let's suppose this is our parent equation, and then we will go by some substitution. I will define another dummy variable tau1 as t minus tau. Fine. Then again we will see what will happen to the limit. So as tau tends to 0, tau1 tends to t. Fine. And as tau tends to infinity, okay, tau1 will tend to t minus infinity, which is basically minus infinity. Okay. Then again tau is equivalent to t minus tau1, which means d tau is equivalent to minus d tau1. So substitute the entire thing here. H of tau के बदले we will write h of t minus tau1. For x of t minus tau, we will put x of tau1, then d tau1, and the limits will be from t to minus infinity. Okay. Then we will rearrange it a bit. X of tau1, then h of t minus tau1 and d tau1. Okay. Sorry, this should have been minus, so minus हम बाहर निकालते हैं, so t to minus infinity, and we will compensate this minus in the limits itself, so it will become it will be reversed with the limits minus infinity to t बाकी तो वैसे बराबर है x of tau 1 h of t minus tau 1 d tau 1. ठीक है, तो to generalize, in general we can say a causal LTI system is given by, या तो आपका जो ओरिजिनल पेरेंट इक्वेशन है y of t 0 to infinity h of tau x of t minus tau d tau, yeah, you can use this one, minus infinity to t x of tau h of t minus tau d tau. Okay, but the important thing here is for an LTI system to be causal, its impulse response should be 0 for t less than 0. Right? Similarly, we will try to express the property of stability for an LTI system in terms of the impulse response. So next we'll be discussing stability of an LTI system. When I say stability, the criteria is the same जो हमने पहले चैप्टर में पढ़ा था. It has to be BIBO stable, bounded input, bounded output. Means you have a system, you give a bounded input, an input which is finite, it should give an output which is finite if it is stable. Right? So let's see what the condition looks like for the stability. So again we'll start with the general expression we have for the convolution, which is this, x of t minus tau d tau, and we'll take magnitude on both sides. So magnitude on left hand side is equivalent to magnitude for the entire integral. Right? Then we have that mathematical inequality, the magnitude of the product is less than equal to the product of the individual magnitudes. Right? So it will be something like this, less than equivalent to minus infinity to plus infinity, but individual magnitudes. It's basically a theorem in mathematics that if you have a dot b ka whole magnitude, it is always less than equivalent to product of their individual magnitudes. Fine. Anyways, now for stability we always give a bounded input. Fine. So let us suppose, because we have to discuss stability, so let's suppose the input x of t is bounded, means is finite by some value, say b, means it has some finite value which is not infinite. So by some value b, it has some finite value b. So जो आपका ये equation आएगा y of t it will be less than equivalent to, this is bounded, so let's suppose it has a value of b that will be a constant outside the integral, h of t d of tau, h of tau d of tau. Fine. Now this is finite, this quantity is finite, and the only way this can be finite is when this integral is finite. Okay, because finite multiplied by finite gives you a finite quantity. अब आपका input, it is bounded by some value b, so it is already finite. So the only term that remains behind is this integral. And if this integral is finite, your output will be finite. So I can say an LTI system is stable if, first we'll see mathematically, this thing minus infinity to plus infinity, magnitude of your impulse response is infinity. Now integral, you know, it basically is it sums up the it sums up this particular quantity between the limits. So in words, I can put that an LTI system is stable if its impulse response is absolutely since it is continuous time, so it is better to write it as integrable, which basically means if this integral after computation is finite, it's not infinity, तब जाके आपका system stable होगा. So we put it like this, that an LTI system is stable if it is impulse response is absolutely integrable. Absolutely integrable means when you integrate it, it will give you a definite finite value. Okay. So these are two important conditions. अक्सर आपके object these typical competitive exams में, GATE exams में, these type of questions are asked. So let us generalize. Causality के लिए LTI system का जो impulse response है it should be 0 for time less than 0. And stability के लिए आपके LTI system का impulse response should be absolutely integrable. Now both these properties are expressed in terms of this impulse response, right? And अगर आपको याद होगा first video in the discussion of LTI systems, I told you that the beauty of this convolution is that it gives you the response of the system to any generalized input x of t without actually having to apply that input. And just you need to know what your impulse response is. और इसमें भी analysis में भी हमने देखा that we can very easily express the properties of a system in terms of this impulse response. And impulse response is what? It is the response of your system to the impulse signal, right? So it has a very high significance, this impulse response, in signals and systems, because it not only helps you to characterize the system, it also defines the property. So मान लीजिए you have a system and you are told that let us know whether this system will be stable or not, Peeble stable. All you have to do is find its impulse response. If it is absolutely integrable, it will be stable. Similarly, if you need to know whether your system, LTI system for that matter, it has to be an LTI system, is causal or not, again, you will go for the impulse response. Fine. Even if impulse response is not given, you will just apply an impulse signal to the system, get the impulse response, and if it satisfies this property that it is 0 for time less than 0 for negative time, you can comment on the causality of the system. So these are impulse. Shows the significance of impulse response. So this discussion, this analysis was for the continuous time LTI systems. Next, we'll be discussing the same thing for the discrete time LTI systems.